This is yttrium oxide. It's a rare earth element which has been bound with oxygen, from lasers to dental ceramics to fighter jets. And it's one of 7 rare earth elements which China this year has restricted the export of.
Most people see polluted rivers as worthless and dangerous. But in several parts of the United States, scientists discovered something hidden in that murky water that no one expected.
With shovels in the ground, Ramaco opens the first new rare earth mine in the United States in over 70 years.
Beneath the rust-colored water and harsh chemical smell, scientists uncovered something far more valuable: rare earth metals.
And here they're drilling for the first time in a decade, going deep to learn more about the rare earths and critical minerals down below.
The very metals used in electric vehicles, smartphones, and modern weapons. And the country that dominates the global supply, China, is watching closely, and it isn't pleased.
It's quite different from the other rare earth element mine, that this is in soft rock, it's shallow, it's easy to access, and the volume of it is simply gigantic.
And we will sell it to domestic customers, and that will be our answer to China.
The shocking discovery inside U.S. rivers. If you had walked along Decker's Creek in northern West Virginia some years ago, the water would not have looked like a place anyone would fish or swim. Locals remember stretches of the creek running a harsh orange color, with rocks stained red and brown, and a sharp metal smell hanging in the air.
The purpose of this is to take the untreated mine water. The water will have a higher pH.
When the water comes right out of the mine into the creek, it's very acidic.
People called parts of it a cesspool, not a stream. Fish were gone, and insects were scarce. That strange color was the first clue that something powerful was happening in the water. The problem came from abandoned coal mines up in the hills. When mining companies cut tunnels into the rock and later walked away, they left behind long walls of broken stone filled with a shiny mineral called pyrite. Pyrite is often called fool's gold because it looks like gold but has no real value by itself. When rainwater and air hit that pyrite over time, a slow reaction starts. The mineral turns into a kind of acid. That acid then eats into the surrounding rock and drags metals out with it. The result is a rusty, acidic water called acid mine drainage that pours out of old mine entrances and seeps straight into nearby creeks and rivers. Acid mine drainage does not just make the water look ugly, it makes the stream hard or even impossible to live in. Even after mines shut down, the drainage can keep flowing for decades because water keeps moving through the old tunnels and waste piles. For years, acid mine drainage in Appalachia was treated only as a curse. It ruined drinking water, corroded pipes, and dragged down property values along creeks that should have been local pride.
The lime slurry pumps through these and goes to the chemical injection manhole where it's injected into the AMD.
It's like filling up a glass as the water, either through groundwater or direct infiltration.
When chemists and geologists started testing that same polluted water more closely, they noticed something surprising. The acid that was ripping metals out of the rock was not only pulling out iron and aluminum, it was also pulling out a group of metals most people never hear about, but that modern technology depends on. These are the rare earth elements.
What we call pyrite and water, you get sulfuric acid and iron.
A set of 17 metals that sit together on the periodic table. They show up in the magnets inside electric car motors and wind turbines, in the tiny speakers inside phones and earbuds, and in guidance systems inside smart bombs and fighter jets. In an extended study of coal mine runoff throughout the Appalachian Basin, scientists discovered that this polluted water and the solids created during treatment can contain rare earth concentrations comparable to certain commercial ore sources. One team of researchers collaborating with the U.S. Geological Survey calculated that coal mine drainage flows in this region transport roughly on the order of 1 million to several million pounds of rare earth elements and yttrium annually, depending on water volume and drainage strength. They noted that this amount could represent roughly a tenth to nearly half of what the United States consumes in rare earths during a normal year. The reason these unusual metals collect in contaminated streams relates to how they act in various water conditions. Rare earth elements tend to remain dissolved and mobile in acidic environments. In a typical clean stream with neutral pH, they are far more likely to stay trapped within rock or soil. In acid mine drainage, the extremely low pH and elevated levels of other dissolved metals allow rare earths to separate from rock more easily and travel with the flow. When that water reaches treatment ponds or wetlands and the pH is increased, those metals can then settle into the sediment at the bottom. Decker's Creek provides a clear illustration of how this happens in real life. The creek flows for just over 20 meters from the hills of Preston County down into the Monongahela River in Morgantown. One of the most severe sources of mine discharge lies at a location called Richard Mine, just upstream from Morgantown. There, abandoned underground mine passages release a constant stream of foul, low pH water into a small tributary. It appears like an ordinary mountain stream. The rocks appear normal. Before treatment, that flow delivered heavy amounts of iron and other metals into Decker's Creek every minute of every day. State and federal agencies, partnering with local organizations, eventually funded a large treatment facility at the site as part of a wider effort to address abandoned mine issues. The plant, which began operating in the mid-2000s, now prevents thousands of pounds of acidity and metals each year from entering Decker's Creek and has helped trout and other sensitive species begin to return. When researchers from West Virginia University's Water Research Institute visited locations such as Richard Mine, they looked beyond the color and odor and noticed something else. They collected samples of the sludge formed when the treatment system adds lime to acidic water and allows metals to settle into a holding pond. In that damp orange mud, they measured how much rare earth metal was actually present. The Institute estimates that sludge from certain southern West Virginia locations can contain about 1.5 pounds of rare earths per ton of dry material. Sites in the northern part of the state can reach nearly 2 pounds per ton. Those concentrations match or exceed the grade of some hard rock rare earth mines overseas. The United States still sources nearly all of its rare earth supply from China and a few other foreign producers, mainly as finished products. Having a domestic source connected to old coal mines represents a strategic opportunity waiting to be developed. What makes this finding more than a West Virginia issue is that the same pattern appears in other mining regions too. Studies in western states, including research on acid mine drainage near Idaho Springs in Colorado, show that water draining from abandoned hard rock mines also carries elevated levels of rare earth elements, which move into solids when the water is neutralized. In other words, polluted streams and treatment ponds across several states are quietly functioning like a network of man-made ore bodies that replenish themselves as long as mine water continues flowing. To understand why this matters, it helps to briefly examine how rare earth metals are typically produced. Conventional rare earth mining often begins with massive open pits or deep underground workings that excavate rock containing only small amounts of valuable metal. The ore must then be crushed, soaked in harsh chemicals, and processed through many stages to extract each element. During this process, miners often deal with radioactive elements like thorium that occur alongside rare earths. These steps increase costs, generate large waste piles, and frequently spark strong local opposition, which is one reason much of the mining and processing became concentrated overseas. In contrast, river systems affected by abandoned coal and metal mines have already completed part of that process naturally. The chemistry inside abandoned tunnels dissolves metals and sends them into nearby streams in liquid form. Existing treatment plants, originally built to improve water quality, already remove metals from that water and concentrate them into sludge. For anyone seeking rare earths, this means the expensive early steps of digging, crushing, and initial separation have already occurred without extra blasting or drilling. The material sits there as a wet, metal-rich mud that must be managed anyway to keep streams clean. Finding hidden metals in river sludge is one thing. Turning those findings into a reliable supply of high-purity material that manufacturers and defense suppliers can actually use is another. That challenge moves the story from river chemistry into the world of full-scale engineering, where the real effort of transforming waste into a new resource begins. How the U.S. turns toxic sludge into valuable metals. Inside a treatment plant, mine water moves into large mixing tanks. Workers add a white powder known as lime, a widely used alkaline substance. Lime reduces acidity and makes the water less aggressive. When this occurs, many dissolved metals begin forming tiny, solid particles. These particles are heavier than water, so they start to sink. The water then flows into tall, circular tanks called clarifiers, where the heavy particles settle at the bottom as sludge, while cleaner water flows over the top and continues onward. West Virginia University's research team went beyond that traditional single-step system. They discovered that moving water through a two-step pH process allows metals to separate in a way that makes rare earths much easier to capture. In the first step, they increase the pH to about 4.5. At this point, much of the iron and aluminum drop out of the water and form sludge, while most rare earth metals remain dissolved. In the second step, they raise the pH further, to around 8.5. That is when rare earths finally fall out, along with other valuable metals such as zinc and cobalt. By dividing treatment into two stages, they can produce a thicker, denser sludge that contains far more rare earth metals than the standard waste produced by old mines. At Richard Mine, this new method is reflected in how the entire plant is designed and laid out. The engineers split the cleanup process into two separate paths. As a result, regular sludge from routine water treatment moves one way, while rare earth-rich sludge moves another. That rare earth stream receives the most protection. The plant pumps this heavier mixture into long white fabric tubes known as geotextile bags, which are laid out in a separate section of the site. These bags function like enormous filters. Water slowly drains through the fabric, leaving behind a thick, heavy mud. Tests indicate that once this mud dries, it can contain roughly 1 to 2% rare earth metals by weight. That represents a massive increase from the tiny trace amounts originally present in the water. Put simply, the plant transforms a nasty orange soup into something far more valuable. A compact, easily transportable pre-concentrate of rare earth metals that can be sent to the next stage of the process. This pre-concentrate is delivered to West Virginia University's Rare Earth Extraction Facility in Morgantown, housed within the National Research Center for Coal and Energy. The United States Department of Energy supported this pilot plant so the nation could test whether rare earths recovered from waste streams like acid mine drainage could become a reliable domestic supply. The facility looks more like a small industrial operation than a university building. Rows of tanks, pumps, steel platforms, and long frames filled with mixing units operate continuously day and night. First, engineers must return the metals to a liquid state, but they need to carefully manage how this occurs. Workers take dried sludge from Richard Mine and combine it with a mild acid, usually a type of hydrochloric acid or something similar, inside heated tanks. The acid pulls rare earths and other metals out of the solid and into the liquid, much like warm, soapy water lifts grease from a pan. After this step, they are left with a strong liquid mixture containing every metal released from the sludge, including the rare earth elements they want and the iron, aluminum, and other metals they do not want. The real separation happens next through a method known as solvent extraction. The term sounds complex, but the idea itself is straightforward. When you pour oil and water into the same glass, they do not mix. One floats above the other. In the pilot plant, one liquid is water-based and carries all the metals. The other is an oil-like liquid that has been adjusted to grab rare earth elements while leaving behind most unwanted metals. The plant sends both liquids through a long series of mixing tanks and settling tanks lined up in sequence. In each tank, workers stir the two liquids together so rare earths can transfer into the oil-like liquid. Then they allow everything to settle until the liquids split back into two layers again. This step is repeated many times. After numerous stages, most of the rare earth metals have moved into the oil-based stream. Once the rare earths are safely contained in that organic liquid, the plant carries out one more switch. It washes that liquid with a clean acidic solution that pulls the rare earths back into water, but now they are much purer than before. After engineers evaporate the water and finish the final chemical steps, what remains is a powder called rare earth oxide. These powders are what magnet manufacturers, battery producers, and alloy makers purchase on the open market. Early pilot systems like this have already produced small batches of mixed rare earth oxide powders with purity levels near 98% by weight. That purity is high enough to show that this method can create real commercial material, not just laboratory samples. When West Virginia University researchers examined acid mine drainage sludge across coal regions, they found that some sites in southern West Virginia held about 666 grams of rare earth elements in every metric ton of dried sludge. Northern West Virginia sites reached roughly 750 grams per metric ton. In simple terms, that equals about 1.2 to 1.7 pounds of rare earth metals in each short ton of waste. Those figures may sound modest, but they match or even exceed some ore bodies mined in open pits overseas. In some cases, the proportion of heavy rare earths in these sludges is especially high, which matters because heavy elements like dysprosium and terbium are the ones the global market struggles to supply. To make the figures even clearer, the team at West Virginia University analyzed the Omega treatment site near Morgantown, which cleans acid mine drainage from an old coal mine. Using real market prices and measured metal levels, they estimated that the rare earth content of sludge at that single site could be worth about $1 million over time if every bit were recovered and sold. When you remember that hundreds of similar treatment systems exist across the region, and many must operate for decades just to keep streams safe, it becomes clear this is not a minor side effort. The Richard Mine plant itself is a large, permanent piece of infrastructure. Bringing power to the site, constructing the treatment building, installing tanks, and setting the clarifiers have cost just over $9 million so far. Most of that funding came from West Virginia's special reclamation funds and federal infrastructure programs because the original mine owner disappeared long ago, and the state is responsible for cleanup. The same trend is emerging at other streams where acid mine drainage has been treated for years. Systems along Three Fork Creek and along tributaries of the Tygart Valley River were originally built only to meet water quality rules, but researchers are now examining them as potential future sources of rare earth feedstock as well. And the idea does not stop in Appalachia. The same two-step chemistry developed by West Virginia University is being applied at the Berkeley Pit in Butte, Montana, a massive toxic lake holding tens of billions of gallons of acidic water left from copper mining. Once you begin turning polluted water into the metals used in electric cars, wind turbines, and modern weapons, you are not just cleaning up old mines. You are entering a larger struggle over who controls these materials. Thanks for watching. Now, check out the videos popping up on screen for more unbelievable stories, and don't forget to subscribe, like, and comment.